And please give a warm welcome to Eloi Sanfèlix and Andres Moreno for CTF Challenges and Solutions. Hi, do you hear me? Everyone? It's too loud or it's okay? It's all right? Okay. Okay, so I'm Eloi. Here's Andres. So we work at Riskier. Has people here heard of Riskier? Anyone? A couple? Okay, I'll just very quickly say, so we do, well, we're an embedded security company. We do security testing of embedded systems. Well, we started with smart cards back in I don't know, 2001 or something with a one-man show, right? And we grew to about 90 people now. We moved from smart cards more towards bigger systems like SoCs for pay TV mostly. But we also are involved with mobile payment and Android applications and stuff like that. So nowadays we cover a bit of the whole spectrum from just pure hardware attacks, not too much invasive, but more glitching and side channel stuff, towards software reversing and exploitation, white box crypto, and a bit of everything. So yeah, we're going to talk about this RHME challenge that we ran a few months ago. How many people have heard of it? Right, enough. Okay, so yeah, I will not say much about ourselves, but before I go on, I'll go with, well, credit where credit is due, right? So the whole team. We started this in 2015 with basically 2 people doing the first edition of the challenge, plus somebody coordinating this. Then they got ideas of making it bigger, 2016, so they got a couple of John Does here without picture. Yeah, so 2 interns, and Rez is one of them as well, one of the John Does. And some more people to make a few more challenges. We put a lot of effort into making a bootloader, and they needed even more people. So in the end, we ended up with quite a bunch of people participating in this, some with more effort, some with less. So first of everything, thanks to all of these people. That's why we're here, actually. So what was this about? So this was an embedded hardware CTF. So it was a CTF, but not so much the kind of CTF that you're used to, where you go to, to Insomnihack and you play for 10 hours. But we wanted to make something more really touching the hardware, right? So what we did is we put a lot of challenges from the usual exploitation, reversing kind of challenges, some crypto stuff, a little bit of black box stuff, and fault injection and side channel attacks on that Arduino. So we had I think 20 or so, many challenges, everything in the Arduino. And this was how this was supposed to work. I don't think you can read it, but on the top here, we do have, basically you had to solve a challenge to pre-qualify. It was a very simple binary, you could run strace or memtrace or something, or ltrace or something and just solve it. But this was more so that not everybody said, I want a free Arduino. But we got many people saying we want a free Arduino. We had a cap of 500, so we had to ship actually 500 Arduinos. Then we sent the boards, and the boards would be personalized with a bootloader. A bootloader that we provided there with some keys that would be used to authenticate and decrypt the challenges. So you could not load those challenges in other Arduinos because that would be too easy in some cases. You could only load it with our Arduino. And that was all based on that bootloader that we put quite some effort on. Now, you can imagine that, shipping 500 Arduinos and putting the little sticker over them and, putting them in these envelopes were, yeah, this took a little bit of time. So we ended up starting a little bit after November 2016. So we extended the deadline to the end of February to give people a chance to play, right? Because we shipped to the Netherlands and then it was 1 day or 2 to ship because we are in the Netherlands, but we shipped to San Francisco and then it took 3 weeks to get there. So yeah, this was not very nice to people, so that's something that we need to learn for next year. But anyway, we ended up extending the deadline. So once you got your board, you entered this panel, and this was a map that one of our colleagues drew. So here is, it's kind of like the Monkey Island map, yeah? You have, yeah, so each of these lands here are territories with the different categories of challenges. So you can see here, you have, for example, the exploitation area. Here you had, where are you? Here you had the reversing area. You had side channel analysis attacks. You had a bit of crypto. And you had up here reverse fault injection attacks. And then there were a few paths across them because that was kind of giving hints of the relationship between challenges, like which one you should do after which one and kind of stuff like that. Anyway, you see quite a few stops here. That's like, I think, was it 22? 22 challenges, plus the bootloader territory here, which was like a special flag without an official solution. But if you broke that, you got twice as many points as with any of the other challenges. So I think everyone solved some, like every challenge was solved except the bootloader. At least as far as we know. I don't know if there is anybody there that solved it, but. So what we're going to do now, we're going to go through a few of these challenges. And we did a selection. We started with some of the reverse engineering challenges, which are linked, which end up in a fold injection challenge. And then we'll move towards some more challenges that are more on the hardware side, and that's what Andres will be discussing. So the first one is this fridge JIT, J-I-T. It's a lot of text. What matters here is that they tell us first, there is a VM running on this thing. And second, you need to crack a password compare routine. That's probably implemented inside that VM, right? And we give you the dump of the firmware and the dump of the data space on the Arduino. So it looks something like this. You get, in the AVR program memory, you get your program here, right? Which is a virtual machine interpreter. This virtual machine interpreter uses the AVR RAM to keep track of its own code and its own data. It fetches an instruction, it decodes it, it executes it, and it writes back to data memory for the registers, etc. So a way to solve this is obviously reverse engineer the VM interpreter, understand enough of how it works, make a disassembler, and then reverse engineer the logic of the password compare routine, which is stored right here. Yeah, that's the normal approach to do this. If you started reversing, actually, you could find that there was some sort of debugger in the board. And this was actually the easiest way to go about on this challenge, was to enter this debugger. And you needed to reverse engineer your way to this. If you press Control-C enough times, you would end up here. It was just in the main loop, you could see like there was a check for Control-C. And if you hit the right moment, then you end up here. And this is actually just a disassembler and a step-by-step execution for you. So you didn't need to do AVR reversing at this stage yet. Or, well, a little bit to figure out, Control-C is a special thing, and then go for it. So this was actually pretty simple code. Once you had this, you could just step through and go one by one and then read the disassembly. It was kind of broken in the sense that one or two instructions were not supported by the debugger. That was on purpose to force a bit of reverse engineering. But it was fairly easy, and you ended up with, you ended up with fairly easy password compares. There was another way, which was even easier, which is the next challenge actually had the same VM, but allowed you to load bytecode. So and then to step into the debugger manually, just right away, without Control-C tricks, with anything. So you could actually just pull the bytecode from one dump, put it in the second challenge, and then reverse engineer it there with the bootloader. That was way easier, but then you needed to figure out where the bytecode was in memory. So so after a bit of reversing, you end up with these few password compare routines that are something like what you see here. So it's just very simple arithmetic, rotate a few bits and XOR with something, and it has to be something else. So that gives you the password. Just fairly standard reverse engineering of password compare. Now, the second challenge was a bit more interesting. That's it's still the same VM, but this time we get told that the password is actually, the flag is actually somewhere in memory. So it's not anymore in the bytecode itself, but you need to actually break out of the VM and read memory of the Arduino. So you need to find a bug to do that. So I try to not put too much AVR assembly here, so that's why I just went to the code. It's easier to see. You can see very, very clearly here that these few instructions, they're just the bitwise and or XOR, all the logic, the normal logic instructions. They didn't actually do any bound checking on the registers. So what you see up here is the R is the register that's encoded in the bytecode. And if you put a number that's higher than the number of registers in this virtual machine, then you get an out-of-bounds access. So how could you exploit this? Well, in this case, you actually need to reverse engineer enough to understand what the VM is like. This VM had 8 general purpose registers, and then followed by, in the same structure and packed together, 2 bytes next to each other, because this is a 16-bit address space. So we had 16-bit registers from 0 to 7. Then the actually these were 32-bit registers actually. So we had 32-bit, 7 32-bit registers, 8 72-bit, 32-bit registers, damn it. Then followed by flags and data, then data length, which is the length of the data memory of the virtual machine, and then code and code length, which is the length of the payload. So you can see here data and code are actually just pointers, right? So if you would smash with register 9, well, 8 because we start counting at 0, right? With register 8, you would smash this guy. Now you can point it anywhere. And now you can use the load instruction in the VM to load memory from this new pointer, for any offset from this new pointer, as long as it's less than data len, right? But you can change it anytime you want. So you can say, I'm going to set it to 0, then load from 0 into a register, and now you read the register. You also got an instruction to print the register through the serial port, so that makes it easier for you to get the data out of the VM. So then you repeat this over and over again until you get the full program memory, the full data memory. So this was my payload. It's just what I said. It's basically preparing, this was, well, my Python code preparing the payload with a Python assembler that I made for when I was testing this challenge for my colleague. Yeah, basically on the top, you see a bit of preparation. I set the register 0 to some counter. I set the register 5 to a step count. And this is because it's not 1 byte, it's OX100, but that's because this is going to be on top. So this is going to be a 32-bit register that will go into the flags and the data pointer. I need to keep the flag 0 so that it just thinks nothing happened. And I need to set the flags, the data pointer 1 byte every time incrementally, right? So I start with these. I then use the XOR operation to clear a few registers. And I use XOR of 8 with 4. 4 contains my original address, with 8 being overlapping with the data pointer. Then I can set up the data pointer. And then I just loop over. So I put the data out and I loop over. I dump the whole flag, the whole SRAM, and then I get the flag. Right? Fairly simple. There is no much code execution yet, just reading memory. Right. So that was one challenge, or well, that was the second challenge. The third challenge, which was called Weird Machine, it was like the same, an iteration of the same, but this time you were told that you cannot read it. Well, you were not told explicitly, but you would find out that you cannot read it with the same technique because the load and store opcode handlers, they were patched. So you couldn't read from the memory space where the flag was. We just put like a blacklist. This area is forbidden for this for the VM, right? So now you really need to use these to get code execution to go around the VM handlers. So yeah, how do you do that? Well, it's AVR, right? Are people familiar with AVR enough? No? Some yes, some no. So AVR is a Harvard architecture. It means that the data is not executable. Data space and program space are separate. I cannot just jump to my data. It's like non-executable data by default, just by design, right? It's not like you don't need to do like page table magic or anything. It just doesn't work. There is no way you can do it. So you really have to do ROP. Okay, you have to reuse the code that's already there to try to make whatever you want to make out of the device. There is a standard way of doing ROP in most systems where you find a stack pivot, which will just make the stack pointer point to your own memory, and then you trigger that, and it will start a ROP chain by using like the tails of different functions, right? This was a way to do this. You could use the opcode handlers. They were a table of function pointers. So that's a very juicy target usually for exploitation. You just go modify that, point it to your stack pivot, trigger that instruction with your bytecode, and then it starts executing your ROP chain. There was an easier way, and an AVR way. So it turns out AVR maps all the general purpose registers on the data memory. So if you write to a certain specific offset in memory, you're actually changing the stack pointer. So that's really nice for making a stack pivot. It's a stack pivot by default, right? It's like you have a write, you have a stack pivot. So basically, you put your payload somewhere in memory, and then you write to this offset that I have in the slides, 5D, 5E, for this particular Arduino. That changes the stack pointer. So you write the address of your ROP chain into that stack pointer memory space, and then when the next function returns from the stack, your ROP chain has been triggered. Okay? So there was one thing, though. I'm used to architectures like ARM and Intel, where the stack pointer points to the next data to be popped. In AVR, it points to the next slot to push into. So it's like off by 1. I spent hours with this. I was like, why does this not work? Why does this not work? Why is it failing? And in the end, it was like, I dumped the stack, and I'm like, stuff seems off by 1. I mean, what the hell? So I just subtracted 1 and it worked. And then I went to the data sheets and I understood why. But yeah, it's sometimes these small differences, they just, they bite you and you spend many hours with these things. Anyway, this was the challenge. This was the official solution. There was another flaw in the VM that we hadn't foreseen, but good that these guys over there, the Hyderabad guys and Balda, found it. Basically, we were checking the bounds in the call instruction. We were implementing something like the Intel call instruction. So you push the return address to the stack. We were checking bounds before the push and not after subtracting 4. So we checked bounds at the beginning, then we subtracted 4, and we pushed into there. What that means is that we can push into -4, and then it's out of bounds. And then you get a one-time write out of bounds with this. One time every time you run the call up, like reset the VM and run the thing. So this actually was easily exploitable because of 2 things. First, memory layout, and second, the fact that we had a loader or a debugger that allowed us to load code again. So in the first step of this, you would have to smash. So you use the underflow. You can see that the data, the VM data, is just after the VM state. So it's just after the code pointer and the code length. So in the first step, you underflow the stack, and it allows you to smash these code and code length variables. So now we can point anywhere we like, the code, right? Now, the second part was the debugger has an option to load new code, which would use this pointer to write the code into. So you got yourself a new arbitrary write, which means code execution in exactly the same way as I mentioned before. So this was the solution that some of the players took, which was slightly different than ours. Wow, I went quite fast.
Yep.
Well, I still have one more. So the next challenge was the same VM, but it would authenticate the bytecode. So it would be like a secure boot kind of thing. The idea was, by looking at what's up there, which it says fault injection, and looking at this reminder that tells people, keep in mind that with fault injection, you might damage your board. The idea was that you would glitch the comparison. So this looked a bit like this. It was, so there was bytecode and 16 bytes of MAC, a message authentication code. This was all in the encrypted bootloader and in the encrypted challenge you got, so you couldn't really reverse engineer the key of the MAC, right? So it went into a MAC, an OMAC with some keys. It checked if they were the same with the memory, like with a time constant compare, so that you couldn't do timing attacks, or at least we think it's time constant. We didn't check, but we checked at the code level, but we didn't time it. I don't know if anybody timed from the players. And if it's equal, it boots the bytecode. If it's not equal, it just says no, right? It's it's a standard secure boot that you get in all mobile phones nowadays or stuff like that. Only instead of using RSA signatures, which is what the majority of systems do, we're running on an Arduino. We cannot do RSA in there because it's just terribly slow and it takes more space than we actually have for actually writing the code. So we did a MAC. So you could glitch there, and then you would get, that was the original solution. Turns out, well, there was an alternative solution, which was instead of glitching there, you glitched during execution. It turns out that our virtual machine had a check when there was an invalid opcode, it would drop into the debugger. Yeah? So what you do is you just load valid code. We gave you, like as an input, we gave you a valid authenticated code. So you load that one with the good MAC, it puts it in, and now during execution, you glitch it. It will decode incorrectly. It will think it's an invalid instruction, and it will say, oh, okay, let's go to the debugger. And now, because you're in the debugger, you can load your arbitrary code and then do the whole exploitation that we did in the previous challenge again. So yeah, that was not fully foreseen by the developer of the challenge, but it was actually obvious after the fact. But anyway, there was yet another surprising solution I think by only Hyderabad, but I'm not sure if other people did it. They actually started, they treat this as a black box. They started tinkering with the data. They saw at the end of the bytecode, there were a bunch of knobs. They thought maybe they are not authenticating the extra padding, but it will get executed. So they started changing it, and they realized, oh, it still boots, even though we changed some data at the end. So yeah, we apparently made a mistake there, and that allows them to run arbitrary code. Actually, we thought, how is that possible? I mean, we're for sure running the Mac over the padding and everything. That was in the code, right? So when I was preparing this presentation, I went to look at the code and like, what the hell happened here? So it turns out this Mac function we were using, which we took from a library, has a message length up here in bits. You can imagine what comes next. Where we call it, we were passing bytes instead. So yeah, this was kind of a big fail. So it was not the padding, it was just the fact that we were authenticating only 1/8 of the message, right? Yeah, but shit happens. Yeah, so these were the first few challenges that were related and we thought were interesting to share. Now, does anybody have questions about these challenges maybe? Or we move on to the other ones? Yes. Yeah. You could do any of them. Both of them work on the Arduino, no problem. You could also do EM glitch or whatever you want, but it's overkill. Sorry? Yeah, I mean, you just drop the voltage a bit and it will, yeah. Yes? No, but I mean, I think it's an AVR 80 Mega 328. I mean, this is not a secure microcontroller. I mean, they are not protecting against glitching at all. That's, I mean, the bootloader survives, so you can do something on top of it. I mean, it seems, but it's an Arduino, and anybody who has reversed an Arduino chip can probably know where to glitch to just disable everything and then get access to the whole thing. So, anyway, no. No, but yeah, no, it's no feedback. Yeah. Anybody else, or we move on? Okay, thanks. Then over to you. You want this?
Let's see if this one works. Hello. Okay. I'm going to show emergency transmitter. That was the hardest challenge we had. It mixed a couple of skills. So it was like 500 points, just below the bootloader. The idea was really simple. You downloaded the binary and you flash it on the board. And when you flash it, you get this message telling you to insert 16 bytes, and the bytes were going to be transmitted encrypted, and that was it. So we actually had to add this node at the end because I think people started glitching and they did not know that they had to extract the key. So they were just submitting bytes at random. So if you find the key, you should be able to encrypt the input and check against the output that you actually got the flag. So how it goes? You write 16 characters, the Arduino LED blinks, and that was it. And that was the whole thing. So yeah, the first step was to connect the Rigol, the oscilloscope, and try to see what was going on with the LED. You will find out that it was Morse code, and yeah, you don't have a decoder for Morse code either in Rigol or whatever, so you have to write your own stuff. And here is a setup from Zeta2. He was trying to decode the Morse code and try to see what the transmission was. He was using here a Raspberry Pi, I guess. And well, that's not a very good idea. You want to do something with a real-time processor such that you know that you're measuring every time the same pace. Okay. It's okay? Oh, yeah. Okay, so the first step, or the first stage of the challenge was actually trying to get the output out of the board. And yeah, start from there and trying to get something out. So after getting output, well, the next thing was, yeah, try to find a buffer overflow, abusing the transmitter, trying to send more data, well, whatever you tried. And if you, yeah, try it enough times, you will see that the transmitter will start behaving weird under certain circumstances. But it was not supposed to, because you should be able to test the key if you get it out. So something funny was happening. If you send enough data, your data will start appearing actually on the output. So you can see here that the beef appears in the output. So you were able to write into the output buffer And you were also able to corrupt the encryption process. But it was not the case every single time. If you just send a little couple bytes after the new line will just trigger the encryption process, then nothing will happen. You will get the same output. So, why is this happening? Well, the book of feature one is that the input is being handled by interruption. It's not being polled. So yeah, we did not disable the interruption, and you can see that it checks for the new line here, and actually it checks for the buffer line here. But if you send a new line, the position will reset, and you will be able to override the buffer. And that way you can see corruption in the encryption. And the second bug or feature was that the input buffer was being used as an output. So Hyderabad has a good test to actually explain this. You can press enter twice, you will get two outputs. And if you encrypt the first output again, you will get the second output. So you will see that this value will remain, the output of the first operation will remain in the input for the second one. So you have two bugs now. That is, the input buffer is being reused for the internal state for the crypto operation, and that you can actually corrupt the data that is on that buffer. So the first idea you have when you can corrupt the encryption process is doing DFA, yeah, differential fault analysis. So yeah, that's a good idea, but you really don't need to do DFA here. You can simplify the attack, and you can just go after the last outround key, right? Because the normal DFA, you don't have control over the value or over the position where you are injecting the fault. So you try to inject before that, and then you do the math from here. But because we know where we are actually corrupting after the new line, we control the position and we control the value of the corruption. So we can simplify the math, and just injecting zeros in just before the outrun key, we can obtain the last AES last run key, and from there we can reverse the key scheduling and obtain the value of the key. So that was the official solution, was attacking the outrun key, and everything was about timing.
Does it work? So basically, I wanted to say the outround key, for those that don't know AES, that's simply an XOR, right? So if you manage to put zeros at the input of the XOR, you get the key out. So that's the last round key. But then you have enough information to wind back to the beginning of the AES and get the actual key.
It's the same as attacking a white box. You try to inject a corruption in the memory and try to get to attack it here so you can get the round key out. But the issue here is the timing. Yeah, you need to send the extra data just before you do the SOR, so you can actually, yeah, get the key out. But doing that at random will not be very successful. So you can know where to inject the fault, because if you inject it too soon, nothing will happen. If you inject here a 0 too soon, then it's like the input never changed. So you will get the very same output, and this means that you just your delay is too short. If you do it too late, then it will appear on your output. So you can actually script the whole process, and if you just get one single output, one single byte in the output corrupted, then that's a result you can use to get the key out. So how the exploitation works, you just connect an Arduino with two UART ports, one to the computer, one to the target, and then you start injecting stuff. And with the colors and yeah, with a filter, you can try enough time until you get the 16 bytes out. The problem is that there's so many bytes that you can add before the outrun key ends. So it was not possible to send 16 bytes to get the last byte before the XOR ended. So you have to actually play it smart, send some bytes, delay, and then send some more bytes to be able to get the last one. And the delay between bytes is also kind of important. So this challenge was all about timing, and that's why like using another Arduino was important. That was the official solution. You just do this with the script, you get the last round key, and yeah, you use the normal scripts on the internet, Git, whatever, and get the key out. You just revert the key scheduling. And the different approaches we saw was Hydrabos tried to do this attack. It seems that it didn't work. I don't know why. So they tried the normal DFA attack, and they only had to inject 4 successful faults on the algorithm, and they got the key out. Balda, he missed, I think, 2 bytes at the end, and he had to brute force those 2. I think that's a timing issue. We did normal DFA and failed. I did normal DFA and failed. I was unable to get the patterns out, and I attacked the last round. So, yeah. And we were expecting someone to use the actually fault injection setup from previous challenges to attack this one, because this one has a little bit of anti-fault attacks countermeasure, but it was possible to actually get the key out with this way, and even with side channel analysis. I want to show also one side channel analysis challenge. I'm going to show the second one. I will explain later why not the first, why not the third one. So the SA2 was, the second challenge was the same as the first one. You just send 16 bytes in. Some encryption process get done in the board, and you get the output. And that was it. We didn't add any command line or anything, so it was actually pretty easy to script the thing, and you don't have to write drivers or whatever. And the second challenge was just the same of the first one plus countermeasures. So you could solve the first challenge with the chip whisperer and just following the tutorials that Colin has in the wiki. But the second one was a little bit more tricky. And I'm going to show how to do it with the chip whisperer, because as far as I know, nobody did the second one with the chip whisperer. I think Hydra used custom tools for that one. And well, I'm not going to use the Risker tool because it's too easy. Or well, I think I have time, so probably I do some small demo. And well, we didn't say that the algorithm was AES 128, but if you hook the scope and you count rounds, yeah, you can actually find out that it was AES 128. So the setup is the normal SCA setup, the chip whisperer. This is live overflow, a Rigel chip whisperer, logic level converter because the voltages were different, a shunt resistor, removing the capacitors. Yeah, that's the normal trace acquisition. And this is Hyderabad, that they went the extra mile to get rid of the noise and all the stuff. So they made their own board to get the traces, and they use a picoscope with the immense amount of memory. Yeah, they went pro on this one. Once the acquisition was done, you can see that there's not a lot to see. There's this trace, well, it looks, full of noise, and you cannot really distinguish anything. You can do a low-pass filter and realize that everything is heavily misaligned. So there's some patterns there. You can see here some spikes in this part, and you can see also here at this part that something is happening. So you need to solve the misalignment first. The attack path, you can try to get the steps from the chip whisperer tutorials, align the traces to the place you want to attack. So if you want to, you can make an educated guess where the Xbox is, and then try to attack that, or yeah, and then attack the Xbox, and it will fail. The thing is that the chip whisper only holds 24K points, so the memory is very limited. And the guy that designed the challenge were like a little bit heavy on the delays, so the S-Box was not captured, was actually out of the picture. And if you try to do the acquisition later, the delays were so heavy that you will have traces with still the Xbox out, or others with the Xbox like previous in the previous window. And as far as I know, the chip whisperer cannot drop traces that are not aligned. So usually what we do at the company, we align the traces that do not align, we drop them, because we know that we cannot get anything useful out of them. And then we solve with the one that align and that we know that have useful information. But as far as I know, the chip whisperer cannot do it. So the solution was not to attack the S-Box as shown in the tutorials and all the documentation, but to actually attack the first key whitening, the first SOR in the first round. So it's not as good as attacking the Xbox, but you will get at least some key candidates. So now the new plan of attack is aligning where the XOR is happening and attacking the out-round key. So you can see here one trace, and you can see at this point where this is the out-round key. These are delays. I will show later the better graphic with you can actually differentiate the delays. And here are actually all the traces that were aligned, and you can see that the very same spikes are like in all the traces. So we know that this is happening in all the traces, and now you can attack this key addition. If you zoom in and you get something like this, you know that you got something useful. You can see there the power change with each of the traces, and all the traces are aligned. So you can perform the attack there. And you will get something like this. So these traces and these results are actually Hydrabus test, and the key is their key. They provided me with the traces. And you can see that, for example, here in these bytes, the key candidates are more or less, has a high confidence. You can more or less guess that is one of those. Same here. But you're gonna have a problem in the 12th byte, and probably also in the 5th one. That is not the probability of those bytes is not that different from the previous one. So you will have to brute force the key. You have some bytes that have more or less the same Hemingway, and here you will have some more, and you will end up with something like this. This is how I did it. Basically, so I just by eye selected the bytes that I thought were worthwhile in the brute forcing, and I just did Python.
So basically what you get out of the DPA attack is a list of scores for each potential key. What you could see in the previous picture, which is not very visible from far, is that the top two candidates for almost every key were quite apart from the next, from whatever is afterwards. So that gives you confidence that one of those two has to be the right key, and you need to combine them.
Yeah, exactly. So yeah, once you have the byte, the candidates, you can just create a script and brute force it. You have the input, the output, and just go all over them, and you will be able to extract the keys. And that's it. That's the second SCA. What was the difference between the side channel analysis challenges? Well, the first one was more or less challenge to get your chip whisperer calibrated or whatever. So it was plain and simple encryption. There were not countermeasures. And we even provided the signal to do the triggering. So you can just hook on the left, and you will be able to trigger exactly where the encryption starts. The second SCA had random delays, and we removed the trigger. So you now had to trigger on the UART line and try to capture there, from there. But yeah, as we saw, the Xbox will move and out of the capture window. And SC3, the last side channel analysis was a little bit more heavy. There was no trigger. The very same random delays from the previous challenge were present, but we added dummy rounds and anti-DFA. So, for example, one of the teams solved side channel 1 and 2, but not the 3. And they solved those two very fast in conjunction with the fall injection one. So we suspect they did the first two with fall injection, with DFA. And the third, because it has anti-DFA, it was not possible. And now, another oops moment, we added the countermeasures on side channel 3 after the first out round key. So all the dummy rounds and stuff were after the first XOR operation. So you can still attack the first XOR operation and get the key out. So it didn't matter. You can attack all of them the same way, and that was it. So yeah, we screw up there. Let's do some highlights. We have several people doing a lot of interesting stuff during the challenge. This is Aries. He made a logic circuit to solve one challenge. So this challenge was called Whack-A-Mole. It's like the game. You just have to walk the moles, and you will get signals on the pins. You have a couple digital pins and stuff, and you needed to interpret that and send the signal at the right time and try to get the mole, right? It was more of a game, not the exploitation thing. And he found that, and he designed a completely digital circuit, no keyboard, no nothing, and it will solve the challenge by its own. So yeah, this was...
So not only no keyboard, no nothing, there is no code running there. It's just pure logic. That's the...
Exactly. This, very good. We have this guy that maybe you know him. He managed to do at least one side channel analysis without having previous experience. Yeah, quite the challenge. And he's doing the write-ups on video, so you can go and search him up. Hydrabus, they made this custom board to reduce the noise. So when, that's beyond duty. What we did, when we were doing the challenges, we tested everything because we didn't want to release something that was not possible to be solved, and that was not possible to be solved with the tools that people had at home. So if you could solve it with riskier tools, yeah, good luck. So we tested this, and when we tested, we removed everything of the board except the processor. Like the UART chip, the LDO, everything. We removed everything, and of course we got really nice traces, and we solved it like right away. And we thought, okay, this is easy. But it turns out that when you have only one board and you're trying to play the CTF, well, you are a little bit more concerned about removing stuff and messing up with it. So the traces were not that good, and the solution they came up with was designing a custom board to reduce the noise and actually get the traces. So the traces that you see before that I used were acquired with this board, as far as I know, I guess. So yeah, this is crazy. And they also, I think they sent a patch upstream to Sim ABR because the UART was not implemented properly. Yeah, so a lot of work. And they also received the award 1 month late and win. Okay, so amazing work. Mr. Macete, this guy made Radare, the compiler for the virtual machine that we did. So yeah, I think he just wanted to show that Radare can do everything. So he got graphs, he got everything running there. So it's amazing work. And he has also really good write-up on the challenges that Eloi explained. The winners, Hydrabus. First, they solved everything except the bootloader. They have like 4 days trying to beat the bootloader. Thanks God, it was not possible. It was not designed to be broken, so it's good. Guys, Valda, Capture the Swag and Sauce One. From these guys, the Balda and guys missed like only 2 challenges, and they solved at least one of each category. So if you pay attention, you will see that there's a lot of skills involved in all the categories we had, and they managed to beat at least one of each one. So this is amazing, and they also played alone. So yes, it's quite a feat. So really good work. We still have one winner to announce, and is the best write-up that is currently being voted, selected. Yeah, so on Risk Your Twitter, you can go, you can find the write-ups, and you can find where to vote for the best write-up. Eloi.
So yeah, so these were a few of the highlights of the challenges and the CTF. Yeah, I mean, we did this to try to get people to learn embedded systems and try to do some of these attacks that people don't really do on their normal CTFs. We had fewer players than boards we delivered, and you know, it's like 80 out of the 500 went to Spain. In Spain, if you say free, then people just jump. I think in the Netherlands also they say, but anyway. But yeah, in the end, we had a few players with high level of skills and with quite good motivation. It's interesting that this ran for like 3 months or so, and some people kept doing it like every evening for 3 months. I would probably give up earlier, but you know, great work for those. Yeah, the team had fun preparing the CTF. We had a few screw-ups, as you've seen, but you know, there's always something to learn. We also, yeah, next year we'll try to prepare earlier and, you know, like learn from these, send the boards earlier and that kind of stuff, because it really takes time. Not only to, I mean, have you ever tried to order 500 Arduinos from China? Fake Arduinos, right?
But still.
I mean, you cannot order 500. People have like 100 and the other one has 50, and then, you know, somebody tells you, yeah, I'm gonna ship them, and they don't ship them, they don't come. Anyway, we'll try to get all these boards way earlier and try to be, like have everybody have the boards at the time the CTF starts, because that was also not, that was a bit unfortunate. And for the challenges, it seems that people had fun with it, so that's good. But we also had some sort of complaints that there was a bit of guessing involved in some cases, and yeah, that we will try to get rid of as well. I mean, in the end, one of the things is for side channel attacks and fault injection, you often really have to guess. I mean, if you're doing a bootloader which is encrypted, that you don't have the ROM and you just want to glitch it, there is no other way than just hook up an oscilloscope, measure the traces, try to figure out what happens and try to glitch it. Or you go the extra mile of getting like a SEM, a scanning electron microscope, and just try to get the bootloader out, right? But that's a little bit of a different level of price range for one to the other. Right, so there will be another one next year. So what we're going to do is we'll have updates on the Risk Your Twitter. It will be around November. It will probably be similar in the sense that it will probably be an Arduino or a similar board that will deliver for free to people. Most likely we'll also allow people to actually buy extra boards if they want. Because, I mean, we had to put a cap, right? Because you're paying these boards. But then if you're glitching them and you kill your board at day one, then you're done. So some people said, well, I would pay for it. I would gladly pay for it if you give me the option. So we'll just probably give the option. You'll say, like, I want 3 more boards, and you pay the cost of the boards, and that's it. And yeah, you can also follow for other stuff. We're putting everything on GitHub. So I said in the beginning there was a bootloader, which was decrypting and authenticating challenges. We have removed that from the challenges now. So we're releasing the challenges without the bootloader. So you can load them on any stock Arduino if you want to play with this. If you want to learn, like, you know, side channel attacks with the chip whisperer, or if you want to make your own setup for glitching or any of that. And all the solutions from all the players are already out there. I think we plan also to make our own solutions in some cases where we think we can provide some additional information. Yeah, and everything will be linked from the GitHub and from Twitter.
¿Hacemos el demo o no? Si alguien se interesa.
No tenemos tiempo.
Okay.
Yeah, so that's it, I think. Well, so that's our our emails and our contacts. As you see there, we're hiring all the time. So if you're interested, if you like this kind of stuff, just get in touch. And if you have any questions, please go ahead.
Hello. Yeah, no questions.
Okay, thanks.
Thank you.